Now that we understand what limits are, we're going to use limits to come up with the definition for a derivative. So we have two different types of lines. We have a tangent line, which is going to have a point intersect the line or curve or graph at exactly one spot. So I could draw in a tangent line right here. That would be a tangent line to my curve. And I'm going to change colors so it shows up a little bit better. I could draw a tangent line into my curve right here. I could draw tangent lines all over my curve. I can also draw secant lines all over my curve. A secant line is going to touch exactly twice. There's an example of a secant line. Here is an example of another secant line. Up until now, every time we want to find slope of a line, we have to use a secant line. We use the formula y2 minus y1 over x2 minus x1. For example, if I looked at this graph here, if I wanted to find the slope of the secant line connecting these 2 points, I could do y2 minus y1 over x2 minus x1, giving me 3/5. But what if I wanted to know the slope of this line? This secant line could be used as an approximation, but as you can see, this slope does not match the slope of this line very well. And in fact, this line has a changing slope depending on what point I'm at. I could do here, and I have a hard time matching up with the program I use. But if I look at the slope of my line, it's constantly changing. So rather than use 2 points, what if I could use 1 point? Well, before I'm able to use 1 point, I have to look at how I come up with my definition. So I'm going to do that exactly what I just did, but instead of using numbers, I'm going to use C. So I'm going to go ahead and I'm going to say that this point right here is C1, f of C1. Remember, f of C1 just means that I plugged C1 into my function. I'm going to say this point right here is C2, f of C2. Again, f of C2 just means the y value that corresponds to an x value of C2. From here, if I wanted to, I could do y2 minus y1 over x2 minus x1. But I'm going to change this just a little bit before I plug it in. I'm going to go ahead and say that I don't know what C2 is, but it's some difference, some change in x from where I was at when I was at C1. So instead of calling it C1 and C2, I'm going to give this point a new name. I'm going to call this point C, and therefore the y value is f of C. My outside parentheses are a little weird. And I'm going to call this point then C plus change of x, okay, whatever this x value is, plus the difference, plus how much I moved, is my new x value. And therefore, my new y value is f of C plus change of x. Okay, now I'm going to go ahead and say this is my x1, y1. This is my x2, y2. According to my formula, my slope is y2, f of C plus change of x, minus y1, f of C, all over x2, C plus change of x, minus C. If I combine my like terms, I get a slope formula of f of C plus change of x minus f of C all over change of x. Remember, C stands for a specific known x value. Ignore this. This is what we're going to talk about in class tomorrow. So now I'm going to use this function to approximate the slope of this graph. Well, hey, that slope still does not match the slope of my given graph. Okay, well, what if I made my change of x a little bit smaller? What if I made this my C2 and used this to approximate my slope? Isn't that a better approximation? Well, what if I made my change of x even smaller still? Isn't that going to be a better approximation? Well, what if I kept making my change of x smaller and smaller and smaller, so small that I get infinitely close to C1. So close that it's almost as if my change of x was 0. So I want to let the change of x approach 0 for my slope function. By doing that, I am going to get the best approximation I can. I am going to get the slope at 1 point instead of the slope at 2 points. That brings to our definition of a derivative. A derivative is the slope of a tangent line. It's a rate of change. It's a rate of change at one point. It's an instantaneous rate of change. So, definition of the derivative, depending on if I'm finding the derivative for a given x value or for a function, is this. So for a given x value, call it c, the definition of a derivative is the limit as the change of x approaches 0 for f of x plus c minus f of c all over change of x. I also need to be able to find the derivative if instead of given a c value, I'm given an actual function value. So if I'm given an actual function value instead, I want to take the limit as change of x approaches 0 of f of x plus change of x, because now I don't know c, so I have to use x instead of a c. Oh, actually, sorry, this was supposed to be c plus change of x. My bad. Minus f of x all over change of x. So it works the same way. The difference is here I have a value to plug in for x, so I'm going to be able to evaluate this for a numerical value, whereas here I don't. I just have to use an x. Same definition, just different circumstances. So let's look at, I think I have two examples here. So let's say I have f of x equaling 3 minus x squared. I need to find the slope of the tangent line at the point 1, negative 2. Well, guess what that's telling me? That's telling me at the point x equals 1 or c equals 1. So I'm going to choose this definition here. And I'm going to say that the derivative or the slope of the tangent line would be the limit as change of x approaches 0 of f of c plus change of x. So I'm going to plug in 1 plus change of x for all my variables, 3 minus 1 plus change of x squared minus f of c. So f of c is my function with my x or my c value of 1 plugged in. So 3 minus 1 squared minus my f of x. I almost forgot this piece of it. This piece of it, I guess, means minus f of c. Oh, no, I had that. I'm sorry. I'm confusing myself. I'm not following my work very well. So f of c plus change of x is right here. F of c is here. I apologize. All over change of x. So now I can simplify this because I can't use direct substitution. So I'm going to go ahead and say that's the same thing as, let's see if I can squeeze it in here, limit as change of x approaches 0 of 3 minus 1 plus 2 change of x plus change of x squared. Yeah, I'm definitely not going to be able to fit this in. Minus, distributing here. Well, actually 3 minus 1 is 2, so just minus 2. Which gives me the limit as change of x approaches 0 of 3 minus 1 minus 2 change of x minus change of x squared minus 2. Again, it's all over change of x. So from here, I combine like terms. Well, I know 3 minus 1 is going to be 2. Minus 2 goes away. So I have the limit of change of x approaches 0 of negative 2 change of x minus change of x squared all over change of x. So I reduce my change of x, and I really didn't give very much room here. I'm running into my next problem, and I get the limit as change of x approaches 0, canceling a change of x from everything, negative 2 minus change of x. So now I can finally use direct substitution. I use direct substitution. I plug 0 in for change of x, and I get negative 2. So the function 3 minus x squared when x equals 1 has a slope of negative 2. So I'm going to erase this just so I have, well, actually, no, I should have room to do this, so I'll just kind of. So this example 2 has 2 points. So now I'm finding the derivative of my given equation, and then I'm going to turn that into the actual equation of the tangent line. So I'll start by finding the derivative or the slope, and then I'll write an equation. So now, instead of being given an x value, I'm starting with by giving just a function. So I'm going to go ahead and use this definition instead. Everything works the same. So I'm going to have, look this way a little bit. I'm going to have the limit as change of x approaches 0 of f of change of x, so 4 of x plus change of x plus change of x, minus 2 minus f of x, all over change of x. Again, I'm going to simplify, which gives me the limit as change of x approaches 0 of 4x plus 4 change of x minus 2 minus 4x plus 2 all over change of x. Well, I see my 4x's are going to drop out and my 2's are going to drop out. Then I can cancel my change of x, and this is just going to be 4. So I see and this should make sense. This is a linear equation. I know the slope is 4, so it should make sense that I get a slope of 4. So I get 4. So now I have to find the equation of the tangent line. So typically what I would do is I would take whatever this gave me and I would plug -2 in for x, but since this is a constant function, I don't have to do that. Well, now that I have a slope and a point, I can say y minus y1 equals m times x minus x1. So y equals 4 times x plus 2. That is review. So the new part is finding the slope. How do I find slope? I use this formula here if I'm given an x value. I use this formula here if I'm not given an x value. They are the exact same thing. One of them I plug the given x value in. The other one I just use a variable.